Our new topic, electricity. So some of you will have done the task from last week where we were reviewing the GCSE content. If you haven't done that, I would suggest that you do go and do that first of all. So over the coming weeks, we will be looking at electricity. And the first bit that we're going to do is looking at current. And actually linking that to charge. And from our specification, it says that we need to know by the end of this, or understand, that electric current is the rate of flow of charged particles, generally electrons, but it doesn't have to be. And you have to be able to use the equation I equals delta Q over delta T, or current is the amount of charge divided by time. Which you've met before, but normally it's written at GCSE in the form of Q equals IT. And we'll be using that a little bit later. Now, before we get started with current electricity, it might be an idea for you to sort of think back to Key Stage 3 and sort of where it all begins, which is with static electricity, or electrostatics. So I'm going to pause, well, I'd like you to pause the video for a second and just jot down anything you remember about static electricity, how things get charged up, what happens when charged objects are near each other. Just do that for a second or two. Okay, so assuming you did that, you've probably got a few things down. Things like objects can become positively or negatively charged. The way things get charged up is through friction, and negative charges generally are rubbed onto or off of an object. And if there's an overall greater number of negative charges than positive charges, you've got something that's negatively charged. And if overall there are less negative charges than positive charges, you have a positive charge. Also, you probably jotted down that those negative charges are basically electrons, because it's the electrons that can move. Other things that you might recall, and this is really important, is that if you have unlike charges, which is just a funny way of saying a negative and a positive charge, they are attracted to each other. And also if you have like charges, so two positive, two negative, they repel each other. That's kind of going to be the basis of how we explain why charges move in the circuits that we're going to look at. Before I move on, I'll just show you a quick picture that I got off a Key Stage 3 website that is not right. I'll just reveal that here. Here we go. I've kind of answered my own question already by saying it's not right. Just quickly, just test yourself. What's wrong with it? That's right. In this, it shows that positive, in fact, it shows lots of things that aren't quite right. So we'll have another look later on. Okay, let's move on. So, first things first. Yes, you've done questions on this stuff before. In your mock exam, you had some electricity questions. I don't know whether you could answer them well back then because I didn't actually teach you back then. So what I want you to do now is you'll find them in Google Classroom. I'd like you to try those questions. Can you do the stuff that you did last year? If you can, we'll move on. So you can pause the video now, have a go at those questions, and then come back when you're done. Okay, welcome back. So if you did that, you might be thinking to yourself, okay, I need to revisit some of these things. And again, this links into the assignment I gave you the other day. You should really maybe make some notes, probably from BBC Bitesize, possibly from the Pixel PowerPoints, on these things: current, resistance, potential difference, what you know about parallel and series circuits, and the definitions and equations. I think you should do that in your own time. It will stand you in good stead for these electricity lessons. Right, now let's move on to something that's on the A-level spec. It's not going to look like it though. It's going to look very primary, in fact. Okay, so I'm going to show you something that we show year 7s. We show year 7s this diagram. Let's see if I can do this. Okay, and we say, oh, can you draw this as a circuit diagram? And the reason I'm showing you this now is I can't check your work while you're at home sketching this stuff down. And I just want to make sure you know the rules now and try and stick to them, that when you are drawing circuits, I'm just going to move myself, here we go. You make sure that we always draw them with right angles. We need to be very, very particular about making sure the wires all join up. And just be very neat when you do it, because we're going to have more complex circuits to analyse later on, and if you're just scribbling them down, it can be a little bit of a challenge to interpret later on. So that was a little aside. Move that out of the way. And now I want to do something that we can't really do in this sort of virtual world. We would normally do a role play of what's going on inside a simple series circuit. So I'm going to talk through what we would have done. You're going to have to use a bit of imagination with this, but I think it's a useful thing to have in your mind whenever you're trying to understand what's going on in electricity. So let's move on. The circuit role play. So I'm going to start off with all of you in a nice big loop. This is what we would normally do in the classroom. And I'd have you all standing around, and I'd say that you represent the charges in a wire. And let me just get a pen so I can draw. Here we go. And I say that at the moment, you're not really doing anything. You're basically delocalized electrons. And you're just sort of swimming around, not really doing anything. You're drifting from one location to the next. And that's what would happen if you had a closed loop of wire. Now, in our role play, actually, you don't represent a single electron. You represent 1 coulomb of charge. Now, a coulomb of charge is a sort of a convenient unit, but each coulomb actually is made up of an enormous number of electrons. So I'm just going to skip forward to show you something and then see whether this makes sense. Do you know what the charge on an electron is? I'm sure you do. It's 1.6 times 10 to the minus 19 coulombs, which means that in 1 coulomb of charge, there are an awful lot of electrons. So 1 divided by that, I think I've done that on the next slide. I'm not even going to attempt to read that number out, but 1 coulomb of charge is that many electrons. So in our circuit role play, here we go, each of you represents 1 coulomb of charge. So many, many, many electrons. And in this circuit, nothing's really happening until we introduce some sort of power supply. So I'm going to introduce a cell. I'm going to use this symbol here, which I'm sure you're familiar with, but a few things about it. You might have forgotten that the longer side represents the positive side and the short side represents the negative side. Okay, and what this does is it basically provides some sort of push that makes the charges move around the circuit. So you start moving like this, drifting around that circuit. And these moving charges we call current. So when we talk about current, we can talk about the flow of charges inside the wire, and the power supply makes that happen. Now, we measure current, you should know this, in amps. which I'm writing over here but not doing a very good job of it. And what an amp is when 1 coulomb of charge passes a point in 1 second. So if each person in the role play represents 1 coulomb of charge, if one person goes past you a second, that's 1 amp. If 2 people go past you per second, that's 2 amps. Okay, right, so we've got this circuit, we've got current flowing around the circuit, but it's not doing anything, it's not serving any purpose. So I'm going to introduce a component. I'm going to introduce a light bulb. Now, this is where we're going to revisit what's going on here at the power supply, because initially I just said, oh, okay, it's providing a push. It's making the charges move around the circuit so we get current. And I'm now going to talk about it in a slightly different way. And you have to hold both of these ideas in your head at the same time. I'm going to say that this power supply provides energy to the circuit. So, as each of the charges goes through the battery, it gains some energy. Now, we call that either voltage or potential difference. And 1 volt is when 1 coulomb of charge gains 1 joule of energy. So 1 volt is basically the same as 1 joule per coulomb of charge. So each of these people have gained 1 joule of energy. And they move around the circuit carrying that energy. Then as they reach the bulb, they transfer that joule of energy to the bulb and it transfers it away as light. And then after, when they come out the other side, they've transferred the energy away, they have much less energy, they have no energy effectively in this circuit. Now again, that's a difficult thing to hold in your head because I'm saying that they've transferred all their energy away, so why are they still moving? These are all simple analogies that help us explain what's going on, help us understand the circuits. So another thing from that is that this is where we get the idea of potential difference from. Because if we've got these people moving around the circuit, or these charges moving around the circuit, and it approaches this bulb, and here this one has got 1 joule of energy, and then it goes through the bulb, and the bulb transfers that energy away. When it comes out the other side, it's got 0 joules of energy. There is a difference. It could do some stuff here, it had potential here, it now can't do anything, so there is a potential difference of 1 volt, of 1 joule per coulomb of charge. So, this actually can then help us explain things like in series circuits, why if you have 2 bulbs, they're dimmer than just 1 bulb in the circuit, because as each charge comes along through here, they will give some of their energy to one of the bulb and some of the energy to the other. Now this does make it sound like they have some sort of agency here, that they're thinking about what they're doing. They're not. Really this comes from the idea of resistance, which is how hard it is to get through the wire. And in our circuit, we're basically saying it's super easy to move through the main part of the wire. So not much work is done, not much energy is transferred getting through that bit of wire. And then you get to the light bulb and it's harder to get through. So it requires a certain amount of energy or a certain amount of work to be done to get through that wire, or the filament of the bulb. And that's why the energy gets transferred away. Now, we're not going to talk about resistance right now, But I think that's enough to get on with there. So what I would like you to do now is maybe rewind this or have another look at it, have another think about it, and then just maybe jot down for yourself a few notes on how you would do a role play and what it would represent to explain what's going on in a series circuit. So you should include at least what the current is and how we represented it, what potential differences, how we represented it, and also I've got some sort of hints and bits and bobs here. So I'll just move this out the way, and you might want to include what current is, potential difference, how the potential difference is shared by the components. So pause this and jot that down for a little while. Okay, welcome back. So let's move on a little bit. So this is something that if we were in class, a couple of you may have asked me about already, because there's something odd here. We need to think about what way the electrons actually move. Now, when we talk about current, we normally think to ourselves, oh, okay, yeah, we go from positive to negative. But you know that electrons have a negative charge. So what's actually happening is that electrons are coming out of the negative, well, they're already in the wire, but they're moving as if they were coming from the negative terminal of the battery, and they're repelled by that because they're both negative, and they're attracted to the positive terminal. Let me just move that. Okay. So they're attracted to the positive terminal. So the electrons move from negative to positive. But you might have noticed earlier on when I was talking about the circuit role play that I was talking about current going this way around the circuit. And the reason for that is that electrons were discovered well after electricity. So when the first experiments were done with electricity and people realised there was a positive and a negative, or they decided to name them positive and negative, they came up with a convention which was that current flowed from positive to negative. It was then very inconvenient later on to suddenly say, oh, actually, it's not doing that, it's going the other way round. They could have swapped everything around, but that would have messed with a lot of the science that had gone on, a lot of the equations and a lot of the things that people understood about electricity already. For example, you might remember this, Fleming's left-hand rule. It would have stopped working. So what they did was they decided to agree that they would carry on thinking about current as if it flowed from positive to negative, and this got called conventional current. But in the back of your mind, you need to know what's actually happening is the electrons go the other way round. That doesn't actually become important to us until we get onto particle physics, when we look about individual particles moving. So for now, you just need to think of current as flowing from positive to negative. There's a couple of illustrations showing what's going on. One, the electrons going towards the positive terminal of this battery, and then this one's showing a little zoom in, showing that the electrons are moving towards the positive terminal. So you might want to jot this down. Conventional current, what we use, flows from positive to negative and flows in the direction a positive charge would move. Electrons flow in the opposite direction, negative to positive. Now, once you've taken that down, have a little look at this. It looks a little bit like chemistry. I think you probably know what this is. Electrolysis. We've got our cathodes and anodes, And why am I showing you this? Well, because in electrolysis, the flow of current isn't necessarily electrons. In fact, the flow of current in this electrolysis here of, what is it, sodium hydroxide, you've got negative chlorine ions, and they're on negative charges, and they flow towards the anode. And the positive hydrogen ions flow the other way towards the cathode. So, in terms of this idea of conventional current, it's the hydrogen ions flow in the direction of conventional current because they are positive charges and they're flowing towards the negative terminal. Whereas the chlorine ions, being negative, flow in the opposite direction to conventional current. I've seen this come up in the exam once or twice. You just need to be familiar with it. Okay, so that's conventional current. And then after this, we're going to look at our definition of what current is. So, moving on. That didn't work. I'll try again. Moving on. So, charge, current and time. Now, I've got a little animation I'm going to show you. I'm not sure how helpful it is, but it took me a while to make, so I'll show you anyway. So, have a look at this. It didn't work. Here we go, and let me present it. And it didn't work. There we go at the start, electrical charge. So just a little reminder what current is. Here's my little animation. There you go. Each of the red dots represents a charge, 1 coulomb of charge, and current is the number of those charges, or the amount of charge passing a point in 1 second. If that's true, current being the number of charges per second, if we wanted to know the amount of charge present, or the amount of charge that's passed a point, we could multiply the number of charges per second by the number of seconds that have passed. Number of charge, sorry, that's hidden a little bit, but it becomes this, that the amount of charge is the current multiplied by the time, and that's the equation that you met at GCSE. Charge is current times time. Now I'm going to just go back to the other presentation. Here we go, and show you this. Charge is current times time, or rearranging that, current is the amount of charge divided by the change in time, or the amount of time that's passed. Now, you want to take that down, but you also want to take down this definition, which is in some ways surprising. I would be inclined, if someone ever asked me to define something, to say, well, because current is moving charge, I would define current in terms of charge. But it's actually the other way round. The SI unit, or the base unit, is the amp. So what we define a coulomb is, we define that in terms of amps rather than the other way round. So the definition is that 1 coulomb is the amount of charge that passes a point when 1 amp flows for 1 second. That is something that you need to learn off by heart and make a note of. So do that now. Okay, I was going to show you this as an example, but it really is a little bit too simple, to be honest. A steady current of 2.5 amps flows for 5 minutes. Find the charge passed at any point in the circuit. The only thing that's going to catch you out here is that it's 5 minutes. You're going to have to change that to seconds. So let's see. There you go, it'd be 750 coulombs. So that's really highlighting that these questions are not challenging. That comes a little bit later. Right, there's one last little thing I want to show you, and then you can do some practice questions on this. And that's this. which is, I don't know if any of you have ever bought, just move that, ever bought a large battery, but they sometimes use unusual units. Actually, you probably would notice this with mobile phones. They often quote the size of the battery in milliamp hours. This big car battery is in amp hours. It's another unit for charge. Remember that charge is current times time. If you've got coulombs multiplied by seconds, we call, what am I talking about? If we've got current multiplied by seconds, we call that a coulomb. But if we want to have like large amounts of charge, I'm just going to stop there because I think I said that wrong a second ago. If we've got amps multiplied by seconds, we call that coulombs. If we want to have large amounts of charge and discuss that, we might use something like this, where 22 amp hours is just a large amount of charge. It's useful because if I tell you that a battery contains 10,000 coulombs, you're not really going to know how long that battery is going to last for. But if you buy a car battery like this that quotes the charge in amp hours, and you know that you're going to use it, I don't know, to run something that you've made that uses 1 amp, you know that it will last for 22 hours. So that's why this can be quite handy. I've just realised I've answered my own questions down here. Okay, so that's it for current, charge and time. Have a go at the questions that are on Google Classroom, and I'll see you next time. Goodbye.